All right, let's take a look at the warm-up. So I strongly encourage you, if you can't get to class a little early and you start that warm-up, that is great. So I'm going to start class by going through it. I'm going to go through it relatively quick. And the idea is the real value is if you can get started, see where you get stuck, right? Seeing where you get stuck, that's really where the value is. All right. So we have an initial value problem here, differential equation, initial condition, and then another question beyond that to use your final solution to find some values of y. You know, you can think this is modeling anything. Maybe y is the population of something, and we have a population at time 1 is 1 million or something. What's the population at time 2? That's the idea here. So I'm looking at that differential equation. Kind of has a familiar form. The first thing I'm going to look for when I see this differential equation is what? Is it exact, right? It kind of looks like it has that shape to it. Let's check to see if it is exact, and I always test first. So the idea is I'm hoping that this piece right here is the partial with respect to x, and I'm hoping this part right here is the partial with respect to y. To see if there really is that capital F, though, I have to check the mixed partials and see if they're equal. So if this is the partial with respect to x, then this mixed partial should be the derivative of this with respect to y, which would give me 1 plus 2y. I'm hoping that thing is fy. Then to calculate fy sub x, I would take the partial of this thing with respect to x. In that case, I would get 1 plus 2y. They are the same. Wonderful, it is exact. Okay. Now I can proceed with that solution process. How do I proceed? Well, if I know that partial of f with respect to x is y plus y squared, then if I integrate that with respect to x, if I do a partial integration with respect to x, I should be able to find what the function is. It should be y times x plus y squared times x. Plus what? Something, right? Plus some other function of y. All right, I'm using psi. Other books will use other things. But there's some other function here. That's my constant, right? Air quotes constant because it's not really a constant. It changes as y changes. But it is constant with respect to x. That's my general form here. Okay, so remember, the whole idea is, here's my solution to an exact equation. It's that thing. It's the function equals c. Well, I have the function. Am I done? Can I just write that thing over there? What am I missing now? Psi. I got to figure out what the psi is. That's the piece that I'm missing. You know, so far I know that yx plus y squared plus x is over here, but I don't know what that psi piece is. So to find psi, I take the f that I have and I calculate the partial with respect to y of it. I will get x plus 2y times x. But I also have this expression for f sub y. That is supposed to be f sub y. So my next step is really to set fy equal to fy. Right? Notationally, that looks a little silly. But the idea is I'm setting this version, the x plus 2yx, sorry. Yep, that's it. Plus, I'm sorry, plus psi prime over here. That's the piece that I was missing. Plus psi prime. That f sub y equal to the other f sub y, which is 1 plus, okay, what am I doing here? Oh, sorry, which is x plus 2yx, right, if I distribute this extra here. Okay. All right. Everybody caught up with me? Does that make sense where that equation comes from? All right, so now I subtract x from both sides. I subtract 2yx from both sides. I'm left with psi prime equals 0. Is that okay? Sure, that's fine. As long as it's not psi prime equals 2x or x squared. As long as there are no x's on that right-hand side, then I'm fine. But if the derivative is equal to 0, then what is psi? Just some constant. Now, do I need to bring that guy up over here and write plus constant? No, right? Because if I put some constant there, I would subtract the other side, and blend the two constants together. So it looks like in this case, that is really my solution. Okay. Kind of a general solution though. So my next step is now use my initial condition to find out what that constant is. So that initial condition basically says that when x is 1, y is equal to 1. So I plug those values in. I get 1 plus 1. That should not be there. I'm just making all kinds of mistakes today. All right, that should just be y times x plus y squared times x. Okay, there we go. Sorry about that. Okay, so I get 1 plus 1 equals c, so c is equal to 2. So my solution is yx plus y squared x is equal to 2. All right. All right. Yep. Yep. Because I got them from two different places, right? I got one from this process of starting with my f sub x, right, this piece up here on the left, and I had to integrate that piece and then take the derivative, and that generated this expression for f sub y. Right. It's basically I have two equations and two unknowns. That's really the gist here. I start with one side, the f sub x, do some stuff to get f sub y, and I compare that to my other side, f sub y. Okay. Other questions? Wonderful. I have a solution here. This is my solution to the initial value problem. Yay! But now I want to figure out what this population or whatever it is at x equals 2. So I plug in x equals 2. So I say since I'm looking for y of 2, I'll have 2y plus 2y squared equals 2. Well, how do I find out what y of 2 is, though? Quadratic formula, right? I'll maybe divide the whole thing by 2. I'll get y squared plus y. I'll have to subtract that piece over. Now I have to use the quadratic formula. So I got y equals negative b plus or minus the square root of b squared minus 4ac minus 4ac, something like that maybe, all over 2a. Negative that guy plus something weird. Something like that, right? But I got two values. Is that okay? Is that all right to do? Yep. Yep. Minus 4ac, yep. I'm not worried so much about specific values. The idea is I have two values for y here. Is that a problem? No, it's not. In fact, I really expect it, right? Because I have this equation here, yx plus y squared x equals 2, and that's my solution, right? But that's also not really a function. In fact, I want to verify this. What might I do? Like if I want to see if I made any mistakes along the way, I can probably plug my differential equation into Mathematica and desolve it. But a lot of times desolve will get you some pretty weird outputs. And that might be hard to really compare to see if you did it by hand correctly. So the other thing I might try to do is maybe plot the direction field. Look at the slope field, plot my solutions, see if they line up and see if that all makes sense. That's a good review of that other process as well. So how do I do that? Well, how do I take this differential equation and figure out how to make a slope field from it? How would I even do that? Solve for dy dx, absolutely, because the slope field says, what's the slope here? What's the slope here? That slope is dy dx. So I take this, I got y prime is equal to, I have to subtract this piece over, divide by the other piece, I'll get something that looks like that. Now I can use this expression for slope to actually make the vector field. So we'll grab this guy up here, I'll do a vector plot. And I'll put in my vector over 1 up the slope. I'll have negative y plus y squared all over x times 1 plus 2y. I will plot that over some range. How about negative a to a? And y from negative a to a. Why am I using a's here? I'm really lazy and don't want to have to change it later and change all those little values. And then lastly, we'll just scale this guy. Vector scale 0.04, 0.04, and none. All right, there is my slope field. Okay. Now I want to see if my solution matches it, so I want to plot my solution. My solution is y times x plus y squared x equals 2. Can I just plot that thing? Can I go plot? I can't do plot because plot expects me to put in a function. I don't have a function here, right? So instead I got to use contour plot. So I use contour plot. And when I use contour plot, I can just type in that equation directly. Yx squared double equals 2. Plot that over the same range. There's my plot. That looks different than I expected. Right, there we go. That looks like I expected, right? I can see it's not a function here. I can see it's really failing the vertical line test. And now to see if it's actually right, I have my two plots. All I want to do is just show the two plots together. So I'll show the first one, comma the second one, and close my show command. All right, I feel a lot better now, right? They really are matching up. And the whole idea is I wanted to find out what my values were when x equals 2. In fact, to see that, I can actually just add another plot to contour plot if I want, and just also plot that second equation, x equals 2. And that will show me that vertical line. And now I can kind of see if those numbers are correct. Any questions about the setup here? Yep. So you factor that 2 out of here, you would get y, factor out 2y, right? You get 2y times 1 plus y equals 2, like that. So then you subtract the 2 over. Right, so it turns out we can't do that. The reason that if this was equal to 0, that we can find the roots like that, is if I have the product of two things that's equal to 0, one of those things got to be 0. That's the only way you can do that. But if I have a 2 over here, there's lots of ways I can have the product equal to 2 there. Okay? All right, good question. Other questions? All right. All right, enough of that mechanical calculation stuff, right? Let's get to the good stuff. Existence and uniqueness, some theorems, a little theory. You guys have been waiting for that since the beginning, right? Right? Not so much? All right, we're going to go through this pretty quickly. The idea for me isn't to go through this section and make sure you're good on the proofs. You can justify this and go through and line by line. The purpose for me, I think it's really important for you as engineers. The idea is you can apply a mechanical process and get some sort of solution, but there are times when that solution will not be correct, will not be reflect the real problem. And so you need to know when your process breaks. When you're finding a solution, but it turns out that solution doesn't even exist then, and you're just making stuff up. Right? You need to know what those triggers are. Because even if you're not doing mechanics, you might take this model, generate an equation from it, put it into some system, and have that kick back a solution. You need to know when that solution is valid or not valid. A lot of times those, Mathematica or MATLAB won't tell you that detail. So that's why you need to know about existence and uniqueness. So we'll go through the theorems in the section and maybe do some applications of it so we can really make sure we're good with it. All right. Big theorem to start off with. For first order, and let me just make a little space here. First order linear differential equations. Linear differential equations. We have this theorem. Now I'm kind of paraphrasing the theorem from the book here. Given some differential equation that looks like that, because if it's a first order linear, we can write it like that. There exists a unique solution. There exists a unique solution. And then I got that weird double arrow. What does that double arrow mean? That guy means if and only if. It's an if and only if. That means that the stuff on the left is true, the stuff on the right is true, stuff on the right is true, stuff on the left is true. It goes both ways. Exists a unique solution if and only if A of t and f of t are continuous. Those are the criteria there. A of t, f of t are continuous. That is really all we are doing. We are checking those guys. Okay? Now your book will write it a little bit differently, a little more formally. And so it really won't say that there exists a unique solution to this differential equation. Really what they'll say is they'll say that maybe given the initial value problem, there exists a unique solution through some initial value. So say x of t0 equals x0. If and only if those two functions are continuous at that point t0, x0. So a lot of this is going to be related to the initial condition. Okay. All right. So we got to check A and we got to check F. Let's see if we can see what that means here. Oops. All right. So we have a differential equation over there. There exists a unique solution to the following differential equation in which intervals? In which intervals does there exist a unique solution? So we have a differential equation there. It's linear, first order. I have to identify my A of t, identify my f of t, in which intervals where there exists a unique solution. And I should start the thing here. There we go. All right, pretty mixed across the boards here. A and D, the early leaders. Okay. Well, what am I doing? Here's my A of t right there. Here is my f of t. I'm looking at the function 2t. Where is that thing continuous? Everywhere, right? I can plug any value of t in there, no problems at all. What about 1 over t? Where is that continuous? Anywhere where t is not 0, right? So I can put positive values in there, right? 3, 5, whatever. I can put negative values, negative 20, negative 18. The only value I can't put in is 0. Right? So I could have a condition that looks like this. I could have a condition that looks like this. The only thing I can't have is a condition that looks like this. Okay? So if I have a condition like this, there will exist a unique solution to this initial value problem. So basically, t can be anywhere in B and anywhere in C. So this one would be B. Okay? Any questions about that? It could be in either of those intervals. Okay? All right, now I'm going to modify the question a little bit. Now we have this problem. We have this differential equation, but subject to that condition. Right? Now we'll have a specific solution. Okay? What is the domain of that solution? What is the domain of that solution? What values can we put into that solution? Right, there's no more constants anymore. Right now we've solved that it's x equals blah, 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 blah. Some function of t over there. What is the domain of that solution? Once again, pretty mixed over here. Could the domain be all of t? It might look like it. Maybe we plug this in. I'm going to make some things up here. We get t squared minus 4t. Hooray! There's our solution, right? I don't really care what that thing looks like right now. What I know is that because my differential equation was discontinuous at t equals 0, my solutions live over here, or they live over here. Now, my initial condition lives in one of those two intervals, which means my specific solution to this initial value problem will live in one of those two intervals, and only one. I could have solutions in either in general, but once you give me that initial value problem, I have chosen an interval. Okay? So this problem would only be C. Okay? Because in general, my solution could exist in either of those intervals, but once you give me that condition, I have chosen an interval. My solution can't jump over the discontinuity that's in the differential equation. Okay? And why not? Well, what is our solution? Think of our solution. It's this function like that, right? And I could certainly plot that function, woohoo, right, whatever it's going to be. But the problem is my differential equation, if I just subtract over that 2tx piece, it's saying the slope is equal to this guy. Which means somehow, whatever solution I'm drawing here, it has no slope at 0, right? And that's the problem. So whatever weird thing I'm drawing here is not correct when I get to t equals 0. So there is some sort of problem. Okay? So the big idea is that that initial condition defines which interval we're working with. Okay? All right. Number two. There exists a unique solution to the following in which intervals? All right, what are we looking like here? Pretty mixed, A or D. All right, why are we mixed? Well, it depends, really. Do we have to put it in standard form or not? And the answer is yes, we do. Right? We have to put it in that regular form so we really know what A of t and F of t is. So in this case, my first step is to divide through by that t so I can write it in proper standard form. I get this is my equation. This is A of t. This is F of t. Okay, so now we can see that this one's going to be D as well. T can't be equal to 0. All right. Any questions about this one? All right, I think that's enough for these ones. All right. What about these functions, or these differential equations? dx dt equals some function of tx. How is this different than our last set of differential equations? Like, why do we need a new theorem here? What's different between this and dx dt plus a of t x equals f of t? Is that just algebra difference or what? What's the difference? Yep. Absolutely. These are linear. These don't have to be linear. They certainly could be, but they don't have to be. So this is a broader group of differential equations that we're looking at now. So go ahead and solve this initial value problem. Go ahead, write this guy out. doing as many of these differential equations as you can. Don't just do the assigned ones, the web assigned. Do all the ones you can find in the book. Find them anywhere else. You probably remember in Calc 1, they were like, derivatives, Bible derivatives, over and over and over again, do as many as you can. Hopefully now you can kind of see why, because it's one small piece of a bigger problem. When you get into a problem, you have to do a derivative, right? Same thing here. One big integration problem, you might solve differential equations several times. You have to separate the variables multiple times to one larger problem. All right, so what do I do here? I go x to the negative 1/3 dx equals 1 dt. I go wham, my integration there. You have to say that when you write your integrals in there, like wow. I integrate. Over here I get x to the add 1 to the exponent, so it looks like I get 2/3 divided by 2/3, the same thing as times 3/2, equals t plus some constant. Multiply through by 2/3. Some different constant. X is equal to 2/3 t plus constant raised to the 3/2 power. Wonderful. Plug in my initial condition. I get 0 equals 0 plus c2 raised to the 3/2 powers. c2 must be equal to 0. Looks like my solution is 2/3 t raised to the 3/2 power. How does that look? And your goal is to be that efficient, right? You just go through the steps. There's our solution. Yay! Right. But what about this? X equals 0 is a function. Right? There's a line that represents x equals 0. Is that a possible solution to our differential equation? If I said let x equals 0, what would the derivative of x be? 0. If I plug that into my differential equation, I would get 0 equals 0. Check. It satisfies the differential equation. Does it satisfy the initial condition? If I plug t equals 0 into my function x equals 0, do I get x equals 0? I do. This is a solution to that initial value problem. But that's a problem for me because now I have this solution and I have this solution, and they are totally different things. So the problem here is I don't have a unique solution to this initial value problem. Okay? Now I didn't have to worry about this before with my linear differential equations. But now that we're looking at nonlinear ones, this is a problem. Okay? It makes nonlinear differential equations much harder. So what do I do here? How do I know if there is a unique solution or if I might get more than one? Well, now I have a new theorem. It makes sense for me to check continuity. Right, if I had dx dt equals 1 over x, I know that when x equals 0, there's going to be a problem. So it makes sense for me to check for the continuity of f of tx. I'm checking to see if there exists a solution. I can check to see if there does exist a solution. As we found the last problem was x raised to the 1/3. Is that continuous? That is totally continuous. Everywhere, right? You plug x equals 0, then you get 0. That's fine. So x to the 1/3 power is continuous for all values of x. But somehow I didn't get a unique solution. And so to solve this, I have this extra check I have to do. I also have to check the partial derivative of f with respect to x. And check to see if that's continuous. If that's continuous, that would be enough to show that it would be unique. That's the extra criteria I need to ensure there's a unique solution. Okay? So one thing I want to stress here, you're checking the partial of f with respect to x, the way we've written it, but more generally, that's the dependent variable. So if I had some other differential equation that was dy dx, right, then you'd be checking the partial of f with respect to y, right? The dependent variable you're taking the partial with respect to. So let's check here. Now let's apply my theorem to my case. What is my f of tx? Well, it's just x to the 1/3, which is continuous. Continuous for all x in R. Let's talk about some notation, right? That probably looks ugly. Couple things. One, up here, I know my handwriting is sloppy, but that is a backwards E on purpose, right? What does that guy mean? There exists. That means there exists. There exists a solution if. Okay. What does upside down A mean? That means for all. For all x, this symbol means belongs to, like belongs to a set, it's in, and that is the set right there of real numbers. Okay. Now, I'm not going to put that kind of notation on a test or a quiz or anything. But you're going to see more and more of it in your later courses. Any questions about notation? Honestly, how many thought might use this backwards, right? All right. So I've identified my function. It's x to the 1/3. X to the 1/3 is continuous. No problems. And sure enough, there was a solution. A solution did exist. But now I have to calculate the partial of f with respect to x. That is 1/3 x to the negative 2/3, which I can rewrite as 1 over 3x to the 2/3 power, right? Which is not continuous at x equals 0. And that was the problem. My initial condition was at x equals 0. And because that partial is discontinuous there, I can't guarantee there is a unique solution. And sure enough, there wasn't a unique solution. Is that partial derivative continuous at x equals 1? It is continuous at x equals 1. I can plug in a 1 there. That's no problem. So if I had changed this to x of 0 equals 1, I would have gotten a unique solution. And everything would have been wonderful. Okay? Any questions about this theorem? You're checking f, and you're checking the partial of f with respect to the dependent variable. Poor problem statement. How about which applies the best? Which of these applies? Here is an initial value problem. Differential equation subject to x of 1 equals 1. Is there a solution to that differential equation, that initial value problem? Does there exist a solution? Maybe there doesn't. There might not exist one. There might exist one, but it might not be unique. Or there might exist a unique solution. Show me which case we're in. Early polling results leaning towards C. People who aren't confident are now changing to C. All right, let's see if that's right. What am I going to do? I got to check what f is. F is this guy. It's 2x squared t. Is that continuous at 1, 1? Sure, no problem. Then I got to check the partial f with respect to x. That gives me 4xt. Is that continuous at 1, 1? It is. Everything is great. New question. What if I change it to x of 0 equals 0? Now what? Does there exist a unique solution? Pretty mixed, pretty mixed. Is 2x squared times t defined at 0, 0? You plug in 0, 0, what do you get? That's fine, right? If I plug 0, 0 into 4xt, what do I get? That's fine too. Perfectly defined. Still good here. Still C. There does exist a unique solution. Okay. What about if I change it one more time to for any x and t in R? Is that okay? That's fine. No matter what value I use for this initial condition, there should be a unique solution. There will exist a unique solution because those values are continuous everywhere. All right, let's look at the next one. And the next one. Once again, you got to think about your form now, right? Our form was dx dt equals some function. Does there exist a unique solution to this initial value problem? Which letter best describes? You will almost certainly see some sort of question on your quiz or exam like this. It's one of those questions that if you know what to do, it doesn't really take any time. I can assess it easily, but I really make sure you know what's going on here. All right, pretty mixed again. A little bit of A, B, and C. What am I going to do? I'm going to check out what F is. F is going to be, well, I got to divide through by T, so I get root X over T. Okay. Then I plug in my condition, 1, 2. Does there exist a unique solution there? Yeah, absolutely. Plug it in, I have no problem. Right, so that would be C. So far, not C yet. So far, I know that there does exist a solution. Now I check the partial of F with respect to X. Okay, check the partial of F with respect to X. I get 1 over T still, and then I get 1/2 X to the negative 1/2. So I can simplify that as 1 over 2T root X. Is that okay when I plug in 1, 2? It is. Right, that one is also fine, so this one would be C. Okay, stop that. Change my condition to X of 0 equals 2. Now which case do we have? Either A or B. Either A or B. Our first thing is just doesn't satisfy the function. Okay. If there's a solution that goes through this point and you're going to draw it, how do you draw it? What's the slope at that point? Right, the slope would be infinite here. Right, that f of xt is basically the slope at that point. Right, because we solve for dx dt. So it'd have infinite slope. I don't know how to draw that guy. Right? Right. So that thing is blowing up there. So that's a problem. So this one, there does not even exist a solution. Okay. Last one, what about this one? X of 1 equals 0. B, but still a little mixed here, right? The idea is there a solution? To do this, we're checking the first thing. That's when we check F. If I plug in t equals 1, x equals 0, what do I get from my value of F? 0. So everything is fine there. So there does exist a solution. But is it unique? When I plug that into the partial here, that's where I have my problem. X can't be 0 for that partial derivative. So the partial is not continuous. That means there's going to be a solution there, but there might be more than one. It might not be unique. So in this case, we have B. Okay? All right, any questions? You guys just look like you're on the edge of your seat. What's next? Wow. We can't wait to hear more about existence and uniqueness. Yep. Right, right. The partial lets us know for sure that it is unique. If it's true, right? But really, now that we see kind of that process, I can just give you that differential equation now, right? Now you can just look at the left-hand side without the initial condition and say, where does there exist a unique solution, right? And I'm looking over there and saying, okay, as long as x is not equal to 0 and t is not equal to 0, as long as all two aren't true, any other condition will lead to a unique solution. So now I really know what regions of the plane I am sure there are going to be unique solutions. Okay? And once again, right, we're also dividing the plane now because I can't have my solutions cross over those discontinuities. Okay? So I can only guarantee that that solution is continuous in those little subregions, right? So now I'm restricted there. All right. Okay, just a quick kind of visual here. It's got two theorems, different groups. And just to make sure we understand here, that first order, this last one, we're checking the partial, that is the more robust theorem. Right? That is the bigger one. That first order linear condition, that's really a subset of the bigger one. And in fact, it kind of makes sense because if you grab this guy and you just rewrite it by subtracting the a of t to the other side, and then think about it. If I look at this guy and apply that first order general theorem to it, when is f of x t continuous? Well, I look over on the right here and say, well, as long as f of t and a of t are continuous, well, then the right-hand side is going to be continuous, right? So that's true. Well, how come then in this linear case I don't have to check the partial? Well, what would the partial of that right-hand side be in this linear case? What is the partial with respect to x, that right-hand side? Just a of t, right? So if a of t is continuous, the partial will always be continuous. That's why I don't have to do a second step when I know it's linear. Okay? So just one less thing I have to do when I recognize the linearity. Okay, this is the fancy theorem from the book. Looks a little bit different than what I've been saying, right? Looks a little uglier. What does all this junk mean? It says that f is continuous on some rectangular region, right? Oh no, what does this mean? Well, it just means this. If I have dx dt equals, say, 1 over t times x, I know that x can't be equal to 0, t can't be equal to 0. If I'm thinking about the plane then, t can't be 0, so that kind of removes that line. And x can't be 0, so it removes the vertical line. So I'm kind of chunked into these big rectangular regions, right? And if I had something else, if I had t minus 1 times x minus 1, maybe that would be the kind of the better image. There's my coordinate system. X can't be equal to 1, so it can't be on that line. And t can't be equal to 1. So now once again I have these kind of rectangular regions that I'm working in. Okay? So if you're in one of those regions and you pick some initial condition right there, some t0, x0, the theorem says that the solution, there will be a unique solution that goes through that point, and that solution, it has a unique solution on the interval, and then it gives us a little window around t. It says that there's some solution that goes through that point. I know that solution is fine, there exists a unique solution, but I only know that that's true inside of this little region around that point. I'm like, oh, what does that even mean, right? It doesn't really mean a whole lot because this next point right here, that point is inside of that region. And so then we could say, well, there exists a unique solution to that point. And then there's another point, and through that point. We kind of connect all those dots to show that my function can be continuous in this whole rectangle. But it breaks down when I get to the discontinuity. And so the whole purpose of this kind of formal statement is just to justify that if I'm inside of the rectangle, I can guarantee there's a unique solution that passes through it, but it is restricted to that rectangle, right? And so I can't extend it across these discontinuities. All right, what does that really mean? Solve that differential equation. Find the solution of that differential equation. Thank goodness for quicker questions. I think you guys are sleeping. I'm going to press that up. started with solving differential equation, make sure you ask before you get started. Anywhere or what technique can you use for this? Is this one separable? Yeah, separable. Let's add our initial condition. X of 1 equals 1. Now we can find our constant. Once you find that constant, approximate x of negative 2. I evaluate my initial condition here. I get 1, C2 minus 1, C2 is 2. Are we happy with this as a solution to our differential equation, our initial value problem? X equals 2t minus 1. Any questions about the separation? Everybody happy with that solution? What is x of negative 2? Wrong. We go x of negative 2 equals negative 4 minus 1, negative 5. Incorrect. Why? If we look at our differential equation and we rewrite it as x prime is equal to x plus 1 over t. Where's my discontinuity? Discontinuity at 0. T can't be equal to 0. I found a solution. This solution is the solution on the interval from 0 to infinity. Because of that discontinuity. My solution looks like it's continuous for all t, but it is not correct to cross over that discontinuity. That is the problem. My solution right now is only on that interval. You can't go through that because even though you have that solution, you want to just draw where the slope for t is equal to 0. Our differential equation is not defined for t equals 0. Okay? When you find that solution, you really should specify the interval that it exists at. Okay? And that's where we run into problems. Where exotic differential equations will be bigger problems. And that's what you need to understand as engineers. Right? You plug that in, you'll probably get 2t minus 1 from Mathematica or MATLAB, whatever you want to use. You need to know that that's restricted to some sort of domain. All right, that's all I got for next time. We'll read through 1.7, and we are going to have a quiz on Tuesday on chapter 1 stuff.